Okay, so let me just review something last week. So last week, actually, great things are here. We basically discussed the linearized Einstein equation, and we've introduced this linearized metric H bar mu nu, where H bar mu nu is defined as H mu nu minus a half eta nu nu times the trace of H. And of course, you guys understand why this is what we want, because precisely that Einstein equation just looks like the usual equations that you have in electrodynamics, and we can just solve it directly. Now, before I ended last time, I gave a very brief description about how many degrees of freedom we have. And I sent you guys a note just giving some details. So let me just review a little quickly the note. So we're talking about a linearized Einstein equation. So what are the number of degrees of freedom we have when we have Einstein equations in a vacuum? In other words, how many degrees of freedom do we actually have for this H bar? And to see this, well, first of all, this is just the definition of H bar, and this is how the de Dunder gauge look like. So importantly, in the de Dunder gauge, when we choose the de Dunder gauge, we have H bar mu nu is equal to 0. So that means that tells you two things. First of all, this tells you that H bar mu nu almost looks like a conserved tensor. And the other is, of course, Einstein. Now the equation of motion, or Einstein equation, tells you that H bar mu nu satisfies box acting on it is 0. So that means that from the equation of motion, we know that we can write H bar as a plane wave expansion, where K satisfies. So here, this K vector here satisfy K squared equal to 0. So this is a null vector, which means that this is a plane. Which means that this is a plane wave that travels at the speed of light. Of course, this is a tensor here, right? So you need some matrix here to carry the tensor indices. So this is some d by d tensor. Now, furthermore, the de Dunder gauge tells you that when you write H bar mu nu in this form, it further tells you that this epsilon mu nu must be transverse. So there's a so the de Dunder gauge, the gauge condition becomes a transverse condition. Gauge condition becomes a transverse condition for your epsilon mu nu. Okay, well, again, this epsilon mu nu is just, so basically you're having a plane wave, but because you're a metric, you're a tensor, so you have this epsilon mu nu, this tensor, which tells you that as something is propagating, how each different components look like. Now, so so this is the frame that we're going to use repeatedly today. So let's set our null vector, our light vector, to look like this. Since null, so it doesn't have a rest frame. So I'm just basically setting it like this way. So what this means is that this is traveling in the z direction. Okay. So this condition, this de Dunder gauge condition, or the transverse condition, then tells us K mu dotted epsilon nu is 0, tells us that basically epsilon nu must take this form. Okay, as you can see, you can just dot this into either 1, 0, 0, 1. Remember that the metric has a negative in the time component, and so all of these are this is the fact that dotted into 1, 0, 0, 1 has to be 0, tells you that these have to be the same. And if you dotted into 1, 0, 0, 1 to be 0, that tells you that these have to be the same. Okay, so the most and of course we note that this epsilon mu nu has to be a symmetric tensor. So this K dot epsilon mu nu equals 0 reduces everything down to just these. So we have A, B, C, D, E, F. So we have 6 degrees of freedom. Okay, so now it's 6 degrees of freedom. Is there any question at this point? Okay. So now since it's, but we're not really done yet. The reason is that now since we're looking at something that satisfies the equation of motion, we can actually, that means that there's actually some transformation on this equation of motion that still preserve the gauge condition. So previously remember that we introduced the Dunder gauge condition in order for us to fix the gauge symmetry. But now, because we're looking at configurations which satisfy the equation of motion, it turns out that usually when you have some things that satisfy the equation of motion, you usually have residual gauge symmetry, which means that now there's some transformation that you can actually do that still preserves this gauge condition. Okay. So remember that since h bar mu nu, the thing that we're looking at is equal to h nu nu minus a half eta nu nu h. You know that we can transfer, so h mu nu under the gauge transformation transfer into h mu nu plus partial mu cosine nu plus partial nu cosine mu, right? So this is, since this is how h transform, we can deduce how h bar transform. H bar just basically, so you have this h piece which just transformed this plus these two terms. And then the trace piece is just, you're just taking eta nu nu over the trace. So that gives you the trace plus this term, which is why you have a factor of 2 here. Okay, and therefore you know that under gauge transformation, h bar transform in this form. So the Dunder gauge condition, which you remember was originally a derivative mu h bar mu nu equal to 0. Under this gauge transformation, the Dunder gauge condition transform into this form. So if the original thing was 0, then the new result can still maintain the gauge condition, which means that it is 0 if box acting on cosine nu is 0. Okay, so if you can find a set of cosine nu that satisfy the box acting on it is 0, then you can do these transformations and you still don't change the gauge. You don't violate the gauge condition. So that means that you can find some cosine with rho, which is, since cosine is just some vector. So it's just rho, which is some vector times exponential I kx. Okay, so again, now this will again satisfy that box cosine nu equal to 0, and therefore this kind of anything that is generated by this kind of transformation, if you change your metric with cosine, where cosine is written in this form, then the gauge condition is preserved. Okay. So when you translate, so if you just take this this form of cosine and then you plug it into the gauge transformation, you'll see that in the end, the result is that remember that or put it into here, remember that your h bar is given now by epsilon times exponential I k dot x. So I'm just throwing away the exponential I k dot x, and because this factor is the same as this factor here. So basically, in the end, you get epsilon nu nu is going to be k, is going to transform like this. Okay, so if rho is just some random vector, then if you just write this out, then this is the form of the change of the matrix. Okay, so what this means is that you can change your epsilon nu nu by this form of the metric. This kind of matrix, and the Dunder gauge condition will not change. So the Dunder gauge condition will still be satisfied if the matrix takes this form. Okay, so since this is something that you can do now, originally we already know that we already fixed our epsilon mu mu down to this form. You'll see that since you can choose your rho 0, rho 3, rho 1, rho 2 to be arbitrary, you can choose rho 1, rho 2 to be opposite, rho 1 to be minus b, rho 2 to be minus c. So when you add the epsilon with this matrix, they cancel. And similarly, you can choose row 0 plus row 3 to cancel A. So you can let row 0 plus row 3 to be minus A. And then you'll cancel this term here too. So basically what I'm saying is that you can choose row 1 to be minus B, row 2 to be minus C. And let's say row 0 plus row 3 to be minus A. So that these terms are all canceled out. Okay. Now you still have something left, right? You still have minus row 3 plus minus row 0 plus row 3 to choose. You can choose this to be arbitrary. So usually what we choose is we choose this. So you notice that this modifies this term here. So basically we choose it such that it cancels the trace part of the matrix. So that, in other words, you make these two component adds to 0. Okay. So this is what I mean last time by if you impose the equation of motion, then your transformation can be used to force that the metric is traceless. So at the end of the day, what you have is that you have a traceless 2x2 matrix, and since it's traceless and symmetric 2x2, it's there's only 2 degrees of freedom here. Okay. Is there any questions? Okay. So that tells you how many degrees of freedom you have in arbitrary dimension. So if you're talking about in any dimension, so if you talk about gravity in d dimensions, so you can do exactly the same thing. So you guys see that all of this is not really restricted to 4 dimension. I mean, and all of this discussion, there's really no constraint on how many space-time dimensions mu nu has to run through, right? So you can write down gravity in arbitrary dimensions. The only difference is that now these epsilon are d times d, and so basically in d dimensions you're going to have your epsilon tensor to be a d times d tensor. And again, the fact that k dot epsilon is 0 will fix you down to something that looks like this form. That's something that looks like this, where all of these things are symmetric. Because you can choose, again, you can choose k to be in the form of 1, 0, 0 all the way 0, 1. And you still have this gauge transformation degree of freedom. And therefore, you can still use that to remove things down to all of these things are 0. You can do exactly the same thing. And then this is just a symmetric traceless tensor. Okay. Therefore, in d dimensions, the degree of freedom is d minus, sorry, in d dimensions, the degree of freedom, so this is d times d, and therefore this is d minus 2 times d minus 2. And therefore, you basically have d minus 2 times d minus 1, because this is a symmetric tensor, and then just minus 1. This is a general formula. So this is a general formula for the number of degrees of freedom you have when you talk about gravity in various space-time dimensions. So of course, we know that when d equals 4, we have, so this is just 2 times 3 divided by 2 minus 1. So we have 2 degrees of freedom. If we have d equals 5, if you think your space-time is 1 dimension higher, then you basically have 3 times 4 divided by 2 minus 1, which is 5 degrees of freedom, and so on and so forth. So you actually have 5 degrees of freedom in your graviton in 5 dimensions. You can actually go lower. So let's say we go to 3 dimensions. So interesting, if we have 2 plus 1 dimension, then what you have is now you have 1 times 2 divided by 2 minus 1. Then you say, hey, I get 0. Okay. And so this is a very interesting thing. So that tells you that they're in three dimension, meaning two, or more precisely 2 plus 1, which you have two spatial and one time component, gravity has 0 degrees of freedom. Or if you fluctuate your metric, the metric has no degrees of freedom. So gravity has 0 degrees of freedom. And for those of you who are more familiar with probably a little bit familiar with mathematics, so basically what this means is that the gravity is that is topological. Okay, it means that since it has 0 degrees of freedom, so that means generically small fluctuations, small deformations actually doesn't change anything, and therefore this tells you that in 3D the 3D gravity is really topological theory. Okay, so there's no propagating degrees of freedom in 3 dimensions. Okay, is there any questions? Okay, one little thing I would like to comment on for those of you who are more familiar with gauge symmetry, which is this: the fact that you have this residual gauge symmetry. You might wonder, and I often like to stress this, you might wonder that, hey, so remember that we have this Dedunder gauge condition, and the whole point was that you use this gauge condition to fix to fix your gauge symmetry. So now you don't have redundant degrees of freedom. But you say, hey, but now I can have a box acting on Cassini. If I find some transformation such that it's a solution to box acting on Cassini equals 0. Now I still have, so you might think that I have unfixed gauge degrees of freedom. I still have this redundancy here. And in fact, it looks like we're actually using this redundancy to remove degrees of freedom. Of course, we're doing this on something that is, we're really doing this on, so let me make 2 points. First, the first point is that what we're really doing here is removing degrees of freedom in our solution to the equation of motion. Okay, this is something that one can do. However, this is not the same thing as we're removing degrees of freedom in your field when the field is in the path integral. So for those of you who've studied quantum field theory, you know that in quantum field theory, the gauge fixing condition is extremely important, because that when you're doing in the path integral, you're integrating over the field. If you don't do gauge fixing, the integration will diverge, because you're going to have you're going to be overcounting the number of the overcounting, or the integral is integrating over these things which are actually the same copies, or you're generating infinity, and therefore you need a gauge fixing condition. Now, in that case, since we're doing the integration over the field, where you're not just dealing with solutions to the equation of motion, you're dealing with arbitrary configuration. Okay, so we're really dealing with arbitrary configuration. Now, even though in that case, if you can find solutions like this, where box acting on Cassini equal to 0, which doesn't change your gauge fixing condition, you might worry that, hey, doesn't this mean that I'm still integrating over things that are redundant? This is not true, because once the requirement, remember that when you, let me just go back to our we can already phrase this in electrodynamic ENM, which is, we know that ENM, when A goes through a transformation, A mu partial mu alpha, we say that this alpha represents an redundancy and an extra degree of freedom, which we need to remove. Now, and we remove this by imposing the Coulomb gauge condition, which is partial mu A mu equal to 0. Now, of course, you immediately see that, hey, but if I choose my alpha, so if I do the gauge transformation on this gauge fixing condition, then my partial mu A mu is going to be changed into partial mu A mu plus box alpha x, right? So we have a similar thing. So you say that, hey, even though I enforce this as 0, but it looks like if I can find alpha x that satisfies box alpha x equals 0, then this is still 0. So that means so this gauge, the fact that I'm forcing this equal to 0 still leaves out these extra degrees of freedom where it just satisfies box alpha is 0. And therefore, I still have extra degrees of freedom that I'm integrating over. And therefore, the path integral is still not well defined. Now, this is not true. The statement I made is not true because notice that here, this must satisfy an equation. So this doesn't have the full functional degree of freedom. The functional degree of freedom is not there because this is a constrained function. Okay, so this does not have the full functional degree of freedom because this alpha net x needs to satisfy this. Okay, and when we're doing the path integral, what we have in mind is we're integrating over fields which are just arbitrary. So the fact that you can still change things by this residual gauge symmetry doesn't invalidate your path integral, okay? Because even though this gauge fixing condition can be maintained if you do this transformation, but this thing here now satisfy that box acting out at a 0, so it's a constrained function. It doesn't have the full functional degree of freedom. Okay, so this is just a side comment for. So these are two different things. Okay, when we're doing path integral, the residual gauge symmetry does not remove any extra degree of freedom. But when we're looking at these solutions to the equation of motion, now you can use these residual gauge symmetry to remove extra degrees of freedom. Okay, so you need to be a little bit careful about these two statements. Okay. Okay, great. So now that we have we have settled the how many degrees of freedom we have. Therefore, we know that now we can look at solutions to the linear Einstein equations more carefully. So first for the vacuum, so let's look at the vacuum. So let's look at vacuum wave. And we already know that if you satisfy the vacuum Einstein equation, you would have h bar mu nu to equal to let me just write it in this form. So we know that okay, first of all, let's write it in epsilon mu nu, and then let's let it propagate. So it has I k. So we already know. So okay, in general we should have I k x, but so we've already chosen our k to be in the z direction, right? So we can write this out. And we know that we can fix things into this form. So this is 0, 0, 0, 0, 0, 0. So I'm just writing out this polarization tensor. And then I have 0, 0, 0, 0, 0, A minus A, B, B. Okay. And then I have exponential minus I omega t plus I, let me call omega z. Okay. Do you guys know why these are both omegas? Can anybody answer?
C equals to 1.
Yeah, because they're like, right? These are like vectors. Okay, so this should satisfy. This is a solution to your Einstein equation, which we just already solved. The fact that these omega are the same are basically reflecting the fact that we already solved the vacuum Einstein equation. And so you see that this is the vacuum wave. Okay, so this is generally how the vacuum wave will look like for something that is traveling in the z direction. So we can look at how things behave. So let's say so here what we're going to think of, what we're going to look at is if you have some things that are spread out, right, and they're just sitting there, so they're in their geodesic, and then this kind of wave just propagates past them, and you want to see what kind of configurations, what happens to them. Of course, for any individual thing here, you won't be, and because of equivalence principle, you won't feel anything, right? If you're just gonna, I mean, it's equivalent to just a free falling observer, right? You're just sitting there, some wave passed through. If it was just you alone, you won't observe anything. So in order to see how things happen, you want to set things up. You want to spread out. You want to have a few things that are spread out, and then you want to see, and then you see how things change as the wave propagates through. So in other words, the configuration we're thinking about is, let's say we have a bunch of things that are set up, and each of them are just following their own geodesic. Okay, so their own geodesics. Okay. And we want to think about how things change when this wave propagates past it. Now, of course, you guys learned this already before. This is basically all you need to do is just use a geodesic deviation equation. Which basically gives, so basically it describes, so let's say when you have a bunch of nearly lying observers and they're related, so we can just parameterize them by S. Each of them, of course, have their own geodesic. So basically you have this function x of mu, tau, and S. So when S is different, you can imagine that there's some kind of a string that is spread across, but each component of the string are not really interacting. There's no tension, so they're just freely lined up, and then so this function will basically ask what is their position for any given time along this S. Okay. Okay, so I think sorry, I should have asked this before. Has geodesic deviation equation been discussed in the class?
Yes.
Okay, great. Then we can just directly use it. Actually, there's some comment. Let me see if there's a question. Okay, great. So since we know that okay, all right. So you guys know what the geodesic equation is. So you know that the velocity at velocity for each point is given by, so let's say u mu tau s. Tau s at given point is of course defined as partial tau x mu tau s. And of course we can talk about also the deviation vector, which is basically defined as partial s x mu tau s. Then the geodesic deviation equation is just given the covariant derivative along for this deviation vector d tau square tau is going to be given by the Riemann tensor. Oh, it doesn't matter. Okay. Good. Now, so let's say so we have these u's here. So let's say everything is at rest. So let's set these things up at rest here. So if we set them up at rest, that means you can approximate at the initial condition for u will be that the u mu will be, for all of them, they're just sitting at rest. So they're all sitting at they're all, we're in this entire thing where we're lining everybody up, and then we're sitting in their rest frame. Okay, so that immediately tells you that this simplifies to, so we're going to do a few simplification. First is setting them at rest. The second is, of course, we're going to do everything linear to h in this class. So if we're doing everything linear to h, so the leading component when you're doing linear in h is, of course, this. So this the geodesic equation to linear order, linear in h. So the leading order is just going to be, so here the leading order is, of course, it just become the usual time derivative. So you just have ds mu dt square. And then here we're basically going to have r mu nu 0 nu, where this is going to add h to the first order. And then these are just 1. So I'm gonna set them to 1, and then this is just multiplied by S nu. Okay. Can someone tell me why do I start with h to the first order and not h to the 0? So remember, what are we doing? We're writing your metric into your
That.
g mu mu into eta mu nu minus h mu nu. So why don't I have the eta part in here?
Because it's 0.
Good, because the Riemann tensor has derivative in it. So actually the leading term is actually already linear in H. So you can plug this in, and it turns out that this is extremely simple. I mean, we've already, so you just have to go through just setting a bunch of things to 0. We have the, I'm sorry, this is taking too long. So, whoa, this is not. Yeah. So remember last time we already written down the linear form of the Riemann tensor. So you just pick these things to be 0. So you can just directly plug it in, and then we will get that this is just equal to a half h dot dot mu nu s nu. Okay. Where now, of course, all we need to do is to plug in this this h dot nu nu. And what is this h dot nu nu? It's exactly this. So we're going to plug in the linear the solution to the vacuum Einstein equation, the linear vacuum Einstein equation. Okay. Now, of course, notice that since we're setting this wave to be propagating in the z direction, so if the wave is propagating in the z direction, you immediately see that this is transverse, since this is x, y, z, right? So this is, in a sense, this is the usual picture that you have, where you have something that is in the z direction, and then you say, oh, then my wave is propagating orthogonal to the z direction. Right, this is very similar to the electromagnetic wave picture that you have in your general physics or even middle school class. So this is seen here. So all of the action is happening perpendicular to the direction in which you're propagating. Okay, and of course, really, this is just because of gauge symmetry and the fact that k dot epsilon has to be 0. But this also tells you that basically the deviation, the vector s, the third component is not going to do anything, because this matrix has only non-zero entry at x and y. So in other words, S3 is not going to do anything, and S0 is not going to do anything. And so all you're going to get is just contribution from S1 and S2. So it's just the x and y directions. So for example, we can just, let's say we just set, for simplicity, let's say if we set this as 0, so you just have the A part. So if we set A to be 0, sorry, B to be 0, if you set B to be 0, then basically what you have, let me just write it out, it says ds1 d2 d square is just going to be minus a half omega square A times S1 exponential. Let me just write this. Okay. I mean, this doesn't matter. I mean, you just have to remember this is just omega t minus omega z. Okay, and you see you have exactly the same equation, ds dt squared, because it's diagonal, except that now you have plus. Okay. So of course, you know that so now you can just solve this equation and solve for s, and basically solve for S1 and S2. And basically you can solve it by let's assuming A to be very small, and therefore you can perturbatively solve it. So you basically just write S1 is equal to, of course, we want to write S1 to some 0 component, but then it's going to be 1 plus a squared and so on and so forth. And of course, once you have a, then you know that this is going to have some exponential I omega t factor here, and then. But importantly, you know that S2 is going to be S2 0, but then relative to S1, this is going to have a minus here. Okay, so what this tells you is that this deviation is such that if it's increasing in the one direction, if it's an increase, so let's say if you start with, so let me just for simplicity, let's say if you have something that is arranged as a circle, you're having these things that are arranged as a circle, then if you're extending in the one direction, let's say if you're expanding in the one direction, in the two direction, it will be contracting. Okay, so it'll be contracting. So you get something like this. Okay, but then the other way, so once it contracts, but once the one direction starts to contract, the two directions starts to expand. So then it expands to this direction. Okay, so in other words, so this mode, so this mode, this A mode here, is basically this A mode, or originally in your tensor here, the polarization tensor here, this A mode here is basically describing when this A mode passes through you, that you're basically start to extend in X and then Y and then X and then Y. So you're going to start doing this kind of extension and contraction. Okay. So it's basically just this kind of contraction. Now, of course, now you know what's going to happen for the other mode. So now you see that there's actually there's various different names, but you see that the A and the B are actually describing different modes of this gravitational wave. Okay, so the B mode. By the way, this is not the same. Actually, it's a little bit similar, but it's not exactly what we mean by B mode. For those of you who've heard about the CMB background polarization, this is not the B mode there. This is just coincident that this is the same B is also describing some kind of rotation. But anyway, so if you do the B mode, then now you see exactly what happened, right? Because this is going to start to rotate, right? Because then your geodesic equation is just d squared s1 dt squared. So let me set a equals 0 and just look at the B mode. Then this is going to be minus half omega squared b, but now it's rotating S2. Okay, and then you have the other. So basically this is rotating your configuration, and for example, in the counterclockwise direction. Okay, so this is like moving things in this direction. So it's like moving things. Okay. So basically the punchline is that you're going to have for vacuum Einstein equation, you're going to get these wave solution, where the wave solution contains 2 degrees of freedom. So one is the usual contraction, and the other is this rotation of your configuration. Okay, this is going to be, we're going to use this shortly. Okay, good. Now let's, so this is just vacuum Einstein at linear order. So now what we're going to do is we're going to do non-vacuum. Okay, so we're going to look at non-vacuum solution. In other words, so we're going to look at non-vacuum solution, which basically we're going to look at gravitational waves coming from a source. Okay. All right. So now, so since we're looking at non-vacuum solutions, so instead of looking at box acting on the H bar mu nu equal to 0, now it's not 0. There's a stress tensor on the other side. So it's just, we're going to normalize it properly with the G mu nu T mu nu. So we're going to have a stress tensor here. And the stress tensor is going to satisfy the linearized, since we're still going to assume, we're still going to assume a translation invariance, and therefore this will still have that it is conserved. So we're going to have partial mu acting our stress tensor to be 0. Okay, so this is still a conserved stress tensor. All right, so now we're going to solve this. So we're going to make things a little bit easier. So we're going to have this. So we're going to have some source here that is distributed, let's say around some. So this is some radius d. So there's some matter stuff happening here, and then it's going to be vacuum all the way. And let's say we're sitting here. Okay, so we're sitting here, and our position is x. And let's say that there's some coordinate x0 that are associated with the degrees of freedom in here. Okay, so as all of you know, since this is exactly the same thing as this equation is exactly the same equation that you will encounter in electrodynamics. Therefore, what you need to do is you just need to use the Green's function. Of course, when you want to use the retarded Green's function, so remember that we just want to have the Green's function. So we want the retarded one. I'm just going to remind you guys what the retarded Green's function is. So of course, Green's function is associated as a solution to this equation. And by retarded, we just mean that we want to only look for, as you know, that these solutions will generally be proportional to exponential plane wave factors. And so basically what you want to do is you want to look for solutions that only involve the outgoing plane wave, and that's the retarded solution. Okay. So I mean, just in case you're a little bit rusty about how to solve this. So first, of course, you know that you can first remove one delta function. So just using that 1 over 2 pi minus infinity to plus infinity d omega exponential minus I omega t minus t naught is going to give us delta function. So we can immediately change this differential equation by removing the time delta function and converting into a Fourier transform. Okay, so basically what I mean is that, so first let's write this out. So let's write this as box minus partial t squared acting on g retarded. So now I'm going to vector x naught and t naught. Right, so we're going to have this, and it's going to be equal to delta 3 x vector minus x naught vector. The time component delta function I'm going to replace this to be 2 pi integral minus infinity plus infinity and d omega exponential I omega blah 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 here. Okay, it's just t minus t naught there. Okay, the reason I want to do this is because then I can make this simple, because you see that this is like an inverse Fourier transform with omega. So you just Fourier transform it back. Then the equation that you want to solve is, so you can make it simpler, which is just omega square acting on g retarded x box not omega, and then you want to solve this as delta 3 x minus x naught, and then exponential I omega t naught. Okay. Is there any questions? Okay, I mean, this is just standard in electrodynamics, so just to remind you. So then once you reduce it to this, we all know what this is. This is just the usual Helmholtz equation, and we can just directly stick in our solution for the retarded solution and retarded solution for the Helmholtz equation. So if you remember that delta x plus omega square g retarded x naught omega is just going to, if you want to solve, this is the usual Helmholtz equation, and therefore the solution to this is just equal to G is just 4 pi x minus x naught and then you have exponential I omega x minus x naught. Okay, and this has a plus in it because we're looking at the retarded. Okay, if you are extremely rusty on this, remember that the solution, since you want to write this as a delta, solve this as a delta function, you can write this in Fourier space. You can write it as this 2 pi 3, and then this will be p square minus omega, sorry, c plus omega, minus omega square, exponential I p dot x. You can write it like this. Then you can immediately see that this is a solution to this equation because box x plus omega square here is going to give you p minus p square minus p square plus omega square, and so it's going to cancel the denominator, and then you're just getting the exponential IPX, and that gives you the delta function. Okay, so you know that this is a solution. So to get from here to here, you just need to do the p integral, and then you can get back this solution that looks like this. Okay. Okay, so since you know that this is the solution, now we can just plug this back in. So we know that this is a solution. So this is a solution if it was a delta function, but now you want delta function times this factor. So you know that the solution is just exponential I omega t naught. So this is the full solution for your retarded Green's function. So then you just go back. Now we want to go back to the original t minus t naught in the original t coordinate system. So you just do an inverse Fourier transform of this solution. So to get this is just now going to be equal to, sorry, I'm just going to erase everything. So just to get back to the original thing that we're interested in, we want this, we just take 4 pi x minus x naught exponential I omega x minus x naught. So we're just going to do the inverse Fourier transform, exponential I omega t naught, and then do the inverse Fourier transform. And then we're going to integrate d omega over 2 pi. This is minus infinity to plus infinity. And so immediately you see that what you're going to get is you're going to get, so this 4 pi comes out. So this 4 pi comes out. Sorry, what am I? 4 pi and then 1 over x vector minus x naught vector. This comes out. And then you're just having a very simple walk in the park integral, which is just this x vector minus x naught minus t naught. Okay. And of course, you all know that this is just a delta function of this guy because we basically started with that. Identity, and so we get the final solution, which is just 4 pi x minus x naught and exponential. Sorry, what am I doing? This is just delta function of x minus x naught minus t naught. Okay, so this is our, this is going to be our, and you can see that this is retarded, right? This is a retarded but the Green's function because of the very fact that, you know, if t is smaller than t naught, this delta function is going to be, the argument inside the delta function is going to be positive. And so this is just going to vanish, right? If t is smaller than t naught, this thing is just going to vanish. And therefore, this is the retarded. You only receive signals when t is greater than t naught. Okay? Okay, great. So now that we find the Green's function, so we have, so what, okay, so once we have the Green's function, so we immediately know that once we have the Green's function, we can immediately solve the equation, right? Because then this tells us, once we have the retarded Green's function, then this immediately tells us that your h bar mu nu is just going to be equal to dx naught to the 4th power g retarded. Maybe it's no longer political correct to say retarded Green's function. I think retarded is a bad word, but anyway. So so let's write the t mu nu and then x naught here. And of course, we want to have minus 16 pi g here. Okay, so you guys see now. So now we immediately have the solution to the Einstein equation. You see that why? Because when the box x acting on h bar, the box x is going to come in and hit this guy here, because this is the only thing that depends on x. And once it hit this guy, it reduces to a delta function, and therefore this is just this delta function. It just localized this x naught integral, and then this and then it's just going to give back us t mu nu. Okay. All right, but since we spend so much time on writing out the retarded Green's function, so we're going to use it. So we can just plug this into here. So since the retarded Green's function has a single delta functions, that means that this integral here over the 4 space-time dimension, there's going to be one direction is going to be localized, and that direction can be chosen. So we can choose it to be, let's say, t naught. So we're going to integrate away the time component. So if we put this into here, then we're just going to be left with a spatial integral minus 16 pi g, and then we're going to integrate dx naught to some the 3 different spatial directions, and then we're going to have 4 pi. Well, actually, the 4 pi we can cancel the 4 pi. So let's cancel the 4 pi, so we get just 4g here. And then we're going to have x minus x naught. And then we're going to have t mu nu, where we're going to have x naught the vector part. And then t naught is going to be localized by this delta function. So we're going to replace t naught by t minus x naught. Okay, so this is the explicit form that we have when we use the retarded Green's function. Okay, and now this x naught integral here, you're integrating over this region here. Okay, good. So do we have any questions? These are just approximation. I think this should be pretty straightforward. But okay, so if there's no question, let's continue. Let me know. You can just if you guys need a break or something, you guys can just drop a message in the chat box. We can have a break. But if nobody stopped me, I'm just going to continue. So now we're going to do approximation. So we're going to solve this by approximating. Since we're basically having to do this integral, but you can see that this integral should be approximated because, well, for one thing, we know that the source that we're looking at is confined to a small region relative to how far we are away from it. Okay, so this is extremely small. So that means that the range of x, so basically the magnitude, so we know that in a sense, the magnitude of x naught, the spatial component, the magnitude of x naught is going to be roughly smaller or equal to d and bigger than 0, right? Whereas for us, the magnitude of x, which is the position of our observer, is going to be equal to r, let me call it little r, and it's going to be much greater than d. Okay, so we're large distance away relative to the size of the object that we're looking at. Okay, so that means that this that means that we can approximate x minus x naught, which of course we know is just square root x square minus 2 x dot x naught minus x naught. So this is not absolute value. This is x naught square this is just going to be equal to let me call this r square root 1 minus a half r x dot x naught minus sorry, this is plus r sorry, this is r squared plus r square x naught. Okay, so you can approximate this as basically r minus x dot x naught over r. Okay, so it's plus higher order terms. So we're going to approximate it like this. And similarly, of course, then we have the inverse minus x naught. The inverse is going to be approximately equal to r plus x dot x naught over r. Okay, good. Now, furthermore, so sorry, let me just get this. Oops. Okay. So furthermore, we know that this T mu nu here, this T mu nu, we can also do an approximation. So we're going to consider T mu nu, or again, this is x naught, the source T minus. So of course now, because we are doing an approximation, we can expand this into T minus R plus, sorry, let me just remind myself that this was a minus sign. So then it's going to be plus x dot x naught over r, right? And of course we can expand this. So we can expand this out to T nu nu x naught T minus r. So we just, this is simple. And then plus T dot mu nu. This is the first time derivative x naught T minus r times x dot x naught over r. Okay. Okay, now we're gonna do a further. So let's say, so now this, whether or not we can drop this term depends on the time derivative of this thing. So of course you guys know what I'm going to do. I'm going to think about some kind of circular orbit things that are circular, the linear perturbations that are generated when you're far away from something that is rotating each other. So if it's rotating each other, then it has some velocity, it has some frequency associated with it. So you know that this T dot here is basically going to be proportional to the frequency. Okay. So we're going to assume that the frequency, so of course this term is, so if we're roughly speaking, this is R, and in terms of absolute value, this is R, sorry, R is already a scalar, I don't need to do this. So in terms of absolute value, this is roughly speaking R d cosine theta, where cosine theta is the relative angular between some x naught and some x. So that means that this is roughly equal to d. So basically, in order for us to drop this term here, in order for us to do approximation where we're dropping this term, we're gonna need omega times d to be much, much smaller than 1. Okay, so what does this mean? Well, that means that d is much, much smaller than 1 over omega. So what is this? So this is the time it takes, sorry. So this is the time scale of change. And this is the time it takes for, we're setting c equals to 1 here. So it's basically the distance is equal to the time it takes for light to go outside of this region D, which means that it's the time it takes for light to something that is light to go outside this region here. Okay, so so if we're dropping this term, what that means is that the amount of time when the approximation we're taking is that the amount of time where, as you guys know, we're looking at the gravitational wave or this wave-like thing which travels at the speed of light. So the time it takes for this wave to propagate away from the source region is going to, during this time, the evolution is slow enough that such a during this time there's actually not much change. Okay, so in other words, so you can this approximation is this evolution is not fast, so that actually when you're talking about the effects that are propagating out, you can almost treat this as a static configuration. Okay, so basically this is the approximation we're taking. So we're basically we're going to take the limit where whatever is going on here, the omega, the 1 over omega is much greater than d. Okay, whatever is going on in there. So this is the approximation. Or in other words, said in another way, for the approximation that we can drop this term, you must be in the regime when this holds true. Okay, this is the requirement that we need to in order to drop that. Okay, so this is the approximation that we're taking. And therefore, this tells us that h bar mu nu is going to be approximately, and this means that we're taking two approximations. First is r is bigger than d, and the other thing is d is smaller than 1 over omega. Okay, so that's what this means. So this is r is much, sorry. So this means that I'm taking, sorry. This means that r is much greater than d, and d is much smaller than 1 over omega. So under this approximation, now your h bar mu mu is just going to be given by 4g over r times integral dx naught to the cube. Remember, so this dx naught to the cube, and then we're going to have t mu nu over x naught t minus r. Okay. Okay. So now remember that the stress tensor satisfies conservation properties, right? It's a conserved stress tensor. So that means that partial t. So we know that since the stress tensor is conserved, is conserved. Since the stress tensor is conserved, we're going to have partial mu t mu nu equals 0, and therefore we're going to have this means that we're going to have partial t acting on t0 nu is going to be equal to partial I on ti nu, right? And therefore you know that the partial t acting on the integral over dx, if you just integrate over the 3 spatial directions over t nu nu, this is just going to be equal to 0 because this is just a total derivative. This is just a total derivative. And therefore, this tells you that this object is a conserved quantity. So this doesn't change with time, right? So from this equation, since the t, in other words, the t0 component, anything that has a 0 is a conserved quantity. So we can call the integration, let's call dx not of t mu t0 0 x naught t minus r. So let's call this e because this is a conserved quantity, and the x naught 0 cube t naught I x naught t minus r, and we'll call this pi. So this is basically the conserved energy and the momentum. Okay, so this immediately tells you that from here to here, this immediately tells you that my h not 0 component is going to be extremely trivial. It's going to be just a far away. This is just 4g e over r, and we're going to have h bar 0I, which is just going to be r 4g pi. Okay, so these components are in some sense the trivial components because they're just related to conserved quantities here. Okay, and of course we can choose a frame, we can choose a rest frame such that pi is 0. Okay, so we're going to have pi equals 0, and then we're just going to have this h bar ee. Okay, so you see that the 0th component of your metric is relatively unimportant or kind of boring at the observer. So as you can imagine, the real excitement is to observe things what's going on? Okay, is to observe things for h bar ij, okay, which of course we know is going to be 4g r, and we're basically going to be interested in the spatial configuration of tij. Okay. Okay. So I think this is probably a good point for us to just take a quick break. So how about let's just take a 10-minute break, and we reconvene at 7:20. Is that good?
Okay.
Okay, great. So I'll stop here. Stop recording. Pause, resume. Yes. Oh yeah. So since I should probably say this again. So for the third problem in our last homework, where we're talking about linear perturbations around the Schwarzschild background, there's going to be a nice trick, which is that we can selectively parameterize your perturbation metric h, the small h, and you expand it on spherical harmonics. So you want to write it as some function that is r dependent and then multiplying spherical harmonics, and then you want to do this expansion. I'm going to send you guys a supplementary material which gives you this kind of parameterization. So it's really about just implementing those parameterization and see how Einstein equation is actually constraining these linear perturbations. So I should say that this is a very nice exercise, and actually this exercise will give you a differential equation which tells you a lot of things. So for example, so basically what this equation gives you is going to give you, once you have the Schwarzschild solution, you're looking at perturbations around the Schwarzschild solution. So for example, it's going to tell you what the quasi-normal modes are around the Schwarzschild black hole. It's going to, as ultimately we're going to look for the tidal forces, the tidal node number. So it contains a lot of information about how the Schwarzschild black hole responds from space-time perturbation. Okay, so these sets of equations are they contain a lot of information. Okay, great. So now back to the business at hand. So now we see that really the juice is in the spatial component of the metric. And so we're going to solve this. So actually it's going to be fairly simple. So we're gonna do a few identities. We're gonna use a few identities where, of course, you guys can all look up. I forgot it was in David Ton's. I mean, this is standard. So we're gonna write these TI. So the punchline is, of course, that TIJ. When you're sitting inside here, is going to be equal to the time derivative of the 0th component metric. Sorry, I already do that. Or let me just write this. Sorry. It's going to be the 2 derivatives times xi, xj plus total derivative terms. Okay, so it's just going to take this form, and therefore, when you plug Tij into here, these total derivative form terms are just not going to contribute, and they're not going, and therefore they're going to be drop out, and therefore you're going to just have this this term here. And so since this is as you know that if we have dipole moments, it's usually described with something that is xi. So this is actually the gravitational quadruple moment. Okay, so this is the quadruple moment. And the reason why it can be written like this is, again, just due to the simple the simple fact that this Tij here is actually a symmetric tensor. Sorry, it's actually a conserved tensor. Okay, so you can always rewrite things using this using the fact that it's actually conserved. So for example, we can write. So let's first begin to show this point that it's just this up to total derivatives. So sorry, so we can write this as Tij. Of course, it's going to be. So we can add total derivative terms here. Tik xj minus kti k xj. Okay, so this is, of course, an identity because this will act on 2 terms. So you're subtracting this term, and then the remaining thing is just this acting on this, but this acting on this is just going to give me delta kj, which is going to give back my original Tij. So this first is just an equality. Okay. But now we're going to use this equality and then use the fact that this is conserved. And therefore, this is just going to give me partial k. So this is a total derivative, of course. And then plus partial 0 ti 0 xj. Okay, so we see that we have a time derivative now. Now, furthermore, we're going to write, so we're going to look at t. So let's look at ti0. Or maybe, let me just, sorry. So I'm going to T0I xj. So we're going to symmetrize this. So by symmetrize, I mean that whenever I write this, I just mean that I'm doing T0I xj plus T0j xi. Okay, so this is what the parentheses mean. So if I have T0I xj, again, I can rewrite this as again a total derivative term. Now acting on T0k xi xj minus partial k T0k xi xj. Okay, again, this is the same reason. This acting on this is gonna cancel this guy. This acting on this is just gonna give back this term. So there's 2 terms because partial k can act either on xi or xj. Okay, great. And then you guys know what I'm going to do. I'm going to exactly use the same thing again. I'm going to use the conservation of my tensor to write this as partial k tik xj plus partial 0 t0 0 xi xj. Okay, great. Now, since Tij is symmetric, I can symmetrize this thing with a half here. So I can just symmetrize it with a half. It's going to be the same because Tij is symmetric. Therefore, I know that my Tij is going to be equal to partial k, blah 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 blah. Where the things that involve in the blah 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 is here. This is going to come into here. And then there's going to be partial 0 acting on Ti0 symmetrized. So this 1/2 of plus 1/2 of partial 0 acting on this symmetrized, but you already know that T0 I xj symmetrized is going to be equal to this. So that means that you just need to partial 0 acting on here. So you're going to get T double dot, which is this 2 time derivative acting on T. Xi, xj. Of course, you're going to have partial 0 acting on here, but then because this is a total derivative, so this just comes back down to here. So it's just going to be total derivative terms here. Okay, so this we've showed that Tij, because of the very fact that this is a conserved stress tensor, therefore Tij you can write it as a total derivative plus the 2 derivative of the 0th component of your stress tensor, and then times xi xj. Is there any questions? Okay, this should be straightforward. And therefore, you can just plug this into here. So once we plug this into here, these terms drop out, and then we just have only these terms left. Okay, so this tells us that our h bar ij is now going to be approximated by r for g. Remember this approximation. This is because r is greater than d, and then d is much smaller than 1 over omega. Okay, so we're going to have this integrated over dx naught to the third, and then we're going to have partial 0 t naught naught a half xi xj. Okay, now so this, of course, this is hij. Now we can use the gauge conditions to get the other components. So from the gauge condition, so from the gauge condition, we know that the partial mu acting on the h bar mu nu must be 0. Therefore, this tells us that the time derivative of, for example, h nu nu has to be equal to partial I h I nu, right? So we can first find that partial 0 acting on h0 I. So let me choose nu to be, sorry, I should use j. If I use this to be j, okay, then this is h0j, then this is equal to partial I hij. But you already know, sorry, these are all h bar. So, but you already know what hij is, right? So you can just directly act this into here. So let me just define, sorry, let me just define I, the quadruple moment, as, let me just define it as dx naught t naught naught xi xj. Okay, so let me just define this as a quadruple moment, so that my h bar ij is going to be equals to 2g over R I ij double dot. So this is much, so then I can write things simpler. Okay, if I write this like that, then this is just going to be equal, so the derivative is hitting on this, so this is just minus R squared 2gxi vector, because it hits on I double dot ij, minus R over 2g I triple dot, and then xi. Okay, remember that what is I? I is integrate over, so integration. So sorry. So remember that my I is basically integration over dx naught to the third power t xi xj. Now, if I write things properly, these are really actually just xi xj, and then this is with t minus r. Right, so this is the retarded time here. So if I'm doing the derivative with respect to r here, when you're doing, because this derivative you're acting on, h bar is just a function of x. It's not a function of x naught. It's just integrating over. So when the derivative is hitting I, it's hitting inside t. Okay, so that's why you get an extra time derivative. You get an extra negative sign because we're really hitting the r here, which has a negative sign here. So that's why you have an extra negative sign. Okay, so this is just right. Okay, good. So this is just this term here, and now we're going to say that this term actually dominates again. So I mean, because of the fact that there's a relative extra derivative here, so that means that this term relative to this term is omega times r. Okay, and we're going to say that omega times r is much greater than 1 in the processes that we're interested in, which is that the r is going to be much greater than 1 over omega. Okay, and the reason is very simple, right? Because this, again, this is the time evolution of whatever the process that you're looking at. This is how much time light takes to travel to you. So of course, we're looking at the sky, and we're going to talk about gravitational waves. So we are going to talk about some things that are circling. And of course, these are billions, millions of light years away from us. Okay, so that means that distance r, of course, is going to be much greater than whatever speed their in spiraling is. So in the regime where we're actually interested in, which is to observe these gravitational waves, this is actually, we're really in the regime where r is much greater, much bigger than this effect. So, but that means that this is the dominant effect. Okay, so we can just neglect this. Okay. So this tells us that partial 0 acting on h bar 0j is basically just going to be given by minus r 2g I 3 time derivatives ij. Sorry. Yeah, this should be lower indices. ij xi. Okay, now since this is also a time derivative, that means that you know that h0j bar now is just going to be r times 2g I double dot ij xi. Okay, plus some integration constant. Okay, and the integration constant can be set by whatever we have here, because initially we've already set that at the beginning, we're setting that the integration time constant pi to be 0, and therefore we are setting that this, so we say that this is actually 0 here. So there's no, the integration constant is set by the conserved quantity that we set up there in the beginning. Okay, and now you can do exactly the same. So now we have, this is just taking nu equals to to j, and then we're solving this. Now we can do exactly the same thing for when nu equals to 0. So we're going to have partial 0 h bar 0 0 equals to partial I h bar I 0. But again, we know that it takes this form. Okay, so we can take the derivative in there. And if you take the derivative in there, this derivative is going to hit this guy. And then this derivative is also going to hit this guy, which gives you a 3 derivatives, 3 time derivatives. And since you have 3 time derivatives, again, due to the same argument of omega r is greater than 1, you know that the 3 time derivative is going to be dominated. And therefore, at the end of the day, you're going to get, so this is just going to be given by r 2g xj hat xi hat and ij 3 time derivatives. And therefore, you know that then you can just solve this immediately. And then we have h bar 0 0 r 2g xi hat xj hat. And then this is ij double dot. Of course, these are functions of now t minus r. And of course, now you have the initial integration constant contribution, which is now 4GB. Okay. Good. So now we have the 3 solutions. So we have the complete solutions to our linearized metric. And now let's look at how these solutions look like. So let's say we're far away from some binary planetary system. Okay, so let's say we're far away here. We're looking at something that is encircling each other. So let's just, for simplicity, make this equal mass. Let's just make this equal mass, and let their distance, relative distance, to be r. Okay, and let's see what kind of gravitational waves we're going to see from the system by solving the linearized Einstein equation. Okay, so what do we do? Well, first of all, let's see if we're setting this thing up. Then in the Newtonian limit, so let's say if these are just very huge objects, which of course we can use the Newtonian limit to describe them, then of course we know that we have the viral theorem, which tells us that this is in classical mechanics, which tells us that the total kinetic energy is 1/2 negative potential. Okay, so the total kinetic energy is of course 1/2 is of course, I mean, each of these are 1/2 mv square. So the total kinetic energy is basically mv square, and minus 1/2 the potential is going to be equal to, the potential is of course going to be rgm squared, right? And of course, from this we can deduce the velocity, because then this is just m times 2r, omega square is going to be, and therefore is going to be equal to this. And therefore you can immediately deduce that omega square is just going to be equal to r cubed. There's a 1/2 here, but there's two times of 1/2 here. So this is going to be 2g big M squared. Okay, so just from classical mechanics, you know that the angular velocity of this system, omega squared, is just going to be given by this. Okay, we're going to use this to estimate the gravitational wave we're going to see. So now let's look at this object here. So of course, then this tells us that we're going to have a t00 component. So the fact that there's 2, let's assume that these are like point-like objects here. Okay, then we're going to say that this is going to be t0. We're going to have a t00 component, and the t00 component is going to be m. So they have 2 masses. We're going to assume that they are rotating in the xy plane. Okay, so we're going to have t00 component, and this is going to be m delta z. Okay, we're just going to look at this effect here, and we're going to look at delta x. So of course we're going to let it. So there's going to be two of them. So one is rotating with a minus sine omega t, and the other is going to be plus r over 2. So basically, I'm treating these things as if they are they are point-like sources. Okay. Okay, great. So should I write down the other component? Do we need the other component? Do you guys think I need to write down the other component? Which component do I need to write down? So from this, which other component do I need to write down? Anybody?
T0J.
Sorry, this is wrong. This would be 2 derivatives. No, we don't need to write anything down, right? Because all we need to, you guys see that all the metric is just in terms of xi, in terms of the quadruple moment, right? And the quadruple moment is just given in terms of integral over the 0, 0 component, right? That was what we were doing all along, right? We were using the fact that you have conserved stress tensor, and the fact you're just integrating over some spatial area. Therefore, at the end of the day, what really only matters just the 0, 0 component. Okay, so this is really why we're going through all this boring derivation. It's just to make that everything just reduces down, the entire system just reduces down to the 0th component that is relevant for the gravitational wave. Okay, so it's really just a 0 component. So I'm already done. This is done. This is all I need. I just need to write down the 0th component of my stress tensor. Okay. And then so, yes.
那个 delta function 应该有一个是一个 x， 一个是 y。
Oh, sorry. What am I writing? Yeah. Thank you. Yeah. Okay. So of course, then we want to compute the resulting quadruple moment. So this is going to be fun. So the resulting, remember what the quadruple moment is. So the quadruple moment is just you're integrating. So these x are really x naughts, right? These are really y naught. These are where the source of this thing is sitting. So remember that we're doing x naught to the cube here, and then we're doing t. So these were initially t naught, but remember that because of the retarded Green's function, the t naught is going to be replaced by t minus r, where t is, well, it's really t minus x naught absolute value, but because we're doing the approximation, so that thing is essentially just r. So we're going to replace t naught equals to t minus r later on. Okay. So so we're basically, so this is t naught. So remember that this is just t naught xi xj. Okay, and now we know that t naught looks like this, right? So this tells you that if x, so first of all, this is really only the spatial components. So this tells you that if xi or xj is in the z direction, then this, because of this delta function, is going to force that component to be 0, right? So this means that this this quadruple moment here is going to look like a matrix that looks like 0, 0, 0, 0, 0. Okay, because anything that has the third direction is going to vanish because of this delta function here. Okay. So if this was x1, x1, so let's say that the 1, 1 component, then x1 is just going to be x. So x is going to be localized to, because of this delta function, x is going to be localized to 2r cosine omega t, right? So x1 is going to be equals to 4r squared cosine omega t, where t is of course going to be t minus r. So let me just write t minus r, or the retarded time square, right? And then of course I'm going to have this m factor here. So basically I know that everything I'm going to have an m factor here, mr squared. Okay, and then I'm going to have 4 times cosine omega squared. So let me just write t as t retarded. So t or tr. So I'm just write tr here. So this is just defined as tr. Okay, this is the retarded time. Okay, and of course, if you do the same thing for y, you're gonna get sine. So you're gonna get 4 sine omega tr. Okay, and similarly, you're gonna. Oh, sorry, my bad. This is not 4. This is actually 1/2. Sorry. Because you actually have two contribution. Okay, so this is 1/2, and this is actually 1/2. Okay, and then this is of course then this is just sine. This is also 1/2 sine omega tr cosine omega tr, and the same thing here. So this is going to be sine omega tr cosine omega tr by 1/2. Okay, so this is going to be equal to this. Okay, so is this clear? Do everyone follow how the gravitational moment is coming from? Is it okay?
Yes.
Okay, great. So we can further of course we can just take this. We can further simplify this. We can take this out. Let's take this 1/2 out and rewrite this, because I want to do time derivative. I'm going to rewrite this as so I'm going to rewrite this as 1/2 1 plus cos 2 omega tr, and then this is of course 1/2 sine 2 omega tr. This is 1 minus cosine 2 omega tr, and this is 1/2 sine 2 omega tr. Okay. So if I write it in this way, then I can easily take the 2 time derivatives. So I'm gonna stay at this page. Sorry. So I'm gonna take the 2 time derivatives, because so remember that my h bar. So we already showed that. Recall that my h bar ij is going to be proportional to r 4g integration over dx naught cube t naught double. Sorry, we don't need to write this anymore because we already have the quadruple the dipole, the quadruple moment form. So it's just going to be 2g I double dot ij. Right? So we're ready. So now all we need to do is just plug this into, so we already have the ij here. So we just need to plug it into here. So now this is just going to be equal to r 2g. So now we're going to have 2 derivative acting on this. And therefore we're going to have, so this is of course you're going to get 4, but 2 derivative, because right, remember that this derivative is with respect to the time which we're actually observing in our position, and this is related to the fact that the time is appearing in the retarded time. And of course, then this is just going to bring down 2 factors of 2 omega, which is going to give you 4 omega squared, which is of course going to cancel these 2 things here. And therefore, we're going to get just m r squared omega squared times the matrix. And the matrix is just going to give cosine 2 omega tr, the retarded time here, and of course sine 2 omega tr minus cosine 2 omega tr and sine 2 omega tr. Okay. And this is the prediction of what this binary object is generating as you're far away and you're looking at it. Okay, and of course we know that we know what the angular velocity is, right? If it's really the angular velocity is given by this term here, and so we can just plug in the angular velocity using this. Okay, so the final thing is that, which is the punchline of today's lecture, is that finally you're going to observe in the spatial direction of your metric something that looks like, so this is r cubed, this is going to cancel this r squared, so you're going to get 4g squared, you're going to observe something there's 4g squared m squared over, did I get the m factors wrong? Is there something wrong with the m factors? There's a factor of m here. Is this m or is this, no, this is m. Sorry, this is not square. Yeah, otherwise the unit is not right. Okay, and then this is just big R times little r times this factor here. Okay, this is negative cos, this is plus, this is sine and sine. Okay, so this is the prediction. So let's see, what does it tell? Well, first of all, you notice that this is exactly the A minus A B B form that we had before, right? This was when we begin this lecture, when we talk about the vacuum Einstein equation. We talked about that you're going to have these solutions where this A is A minus A and then BB form here, which basically tells you 2 different polarization modes. So the prediction is, of course, that you're going to observe exactly 2 polarization modes. Okay, because it's going to both generate both the cosine or the A mode and as well as the B mode. So both of these are going to be present. This is the first prediction. The other prediction is the magnitude of this thing. So you notice, so not surprisingly, as the distance, so remember R was the distance between the 2 massive objects, which they're circling with each other. So the smaller the distance and the bigger the mass, the bigger the magnitude that you're going to observe, which of course is again as expected. So this is why if you look at the amplitude, you see that as they start to go in closer with each other, the amplitude is going to start increasing because of this 1 over R factor here. Okay, so this is the highlight of today's lecture, is that we've derived the gravitational wave that we observe for a binary object. So next week, we're going to talk a little bit more about the physics of these gravitational waves. Yeah, and we're gonna and I think that we need to discuss we can discuss a little bit about what else you guys want to hear. Do you guys want to after this, do you guys want to talk about for example, how to include one proposal is to talk about this more formal aspect of GR, which is basically how to couple do what is called the VO bind and the spin connection formulation, which really makes GR more universal in the sense that it can couple to arbitrary spin fields, including quarks, gluon, electrons, and make it more consistent with more in the language of particle physics. Or, for example, you guys want to hear more about cosmology or whatever things that you guys want to talk about more. But next week, we're going to have a small discussion about the other aspects of gravitational physics, and then we're going to move on to other directions that you guys might be interested in. Okay? Okay, so this will be the lecture that we have today. Is there any questions?
老师，我可以问一下上一份那个作业 Penrose diagram 可以讲一下吗？
Okay. 所以sorry 有点 so I guess sorry 你们是有什么问题 okay sorry let me just okay so I guess you guys are asking about the Penrose diagrams. I mean it's the same thing, right? So once you go to the Kruskalov coordinates, then you want to use this arctangent U and arctangent V, right? And I think that you immediately get this kind of picture, which you get this kind of you first get this picture, right? Let me see. Sorry. Let me just find it. Right, I think that's sorry, let me just draw this. So I think usually what you will get is you will get first, you know that the R equals 0 singularity is here, right? And therefore you have the horizon that is going here, and you're going to get the spatial infinity here, and this is the diagram you get, right? And this is the horizon R equal RS, Short-shell horizon. So getting this, was there any problem in getting this?
没有。
Okay, so then of course then we analytically continue, and we know there's the other copy, right? So there's the other copy, which is this guy here, and so this is essentially this diagram, up. So you flip this into here, and of course then you extend this the horizon here, and then you get this other. So the other piece here, right? And we have so this is this piece, and this piece is opposite, right? And so of course this is the R equals 0, and this is of course R equals 0. So we're basically just flipping this and then gluing these things together. So what exactly is the question?
我想问一下关于红色那部分的
Yeah.
no infinity 要怎么定义啊？
Oh, I see. So of course we can define our so the question is that, okay, I see. So you guys are asking since we know that this is Gr plus here, right? And this is Gr minus here, right? And this of course this is I plus and infinity, and this is I minus, and this is the singularity at the origin. How do we define Gr plus? How do we determine which one is Gr plus and which one is Gr minus? Of course, this is just a choice that you can do, and because you're taking literally two different regions and you're just gluing them together. And the natural, precisely because you're gluing these things together, you know that everything here is propagating to R, where this R0 is at your future here. So if you want to have this to be consistently glued with this one here, this is sitting at the future. So that means you want the time coordinate system here such that here this is Gr plus, because then if this was Gr minus, then this doesn't make any sense in this gluing, because this is sitting here at the future, and then all of a sudden this going to here, you have this I minus here, which is not a consistent gluing of the time directions. So you want to, so because of the fact that you already set this R0 to be continue from here to here to be always in the future. And so the natural thing you want to do is you want to have here to be scribe plus, so that this is naturally from I plus to I plus here. Okay, this is really, you're taking two different sheets and you're actually gluing them together, and then you orientate, or you're choosing your, you can choose your orientation that is more consistent with the gluing.
所以这跟coordinate time 没有太大关系嘛？
Yeah, I mean, this is just, you're just glue. I mean, this is a gluing. This is a gluing. So there's always a prescription for how you're gluing the different patches together.
哦，好，谢谢教授。
Yeah. So this, so in other words, said in another way, there's actually no way of continuing from here to here. Okay, because these are just glued patches. Okay, so I don't know. Sometimes people call this a parallel universe or something.
哦，OK，
Okay, but this is really the reason why you have scribe plus here, is because you already have that, you have spatial infinity here. Sorry, you have the singularity in your future here. Okay, so if there's no question, then I guess we'll stop here.